Arthur Dent sat in the dimly lit control room of the Heart of Gold, nursing a cup of something that was almost, but not quite, entirely unlike tea. The infinite improbability drive had just deposited them in a nebula that looked suspiciously like a giant rubber duck, and Arthur was feeling particularly out of his depth. "Ford," he said, staring at the swirling improbabilities on the screen, "what exactly is going on here? 1 minute we're hitchhiking through space, the next everything's approximate. Like the universe can't decide what it wants to be." Ford Prefect, lounging against a console with a towel draped over his shoulder, looked up from his copy of The Hitchhiker's Guide to the Galaxy. "Ah, Arthur, my primitive earthling friend, you've stumbled upon the essence of domain theory. Pull up an improbably comfortable chair." "Domain what?" Arthur blinked. "Domain theory," Ford explained, waving his hands as if conducting an invisible orchestra of Vogons. "It's the mathematical backbone of how the universe handles all this infinite nonsense without imploding. See, in the grand scheme of things like programming the galaxy's most absurd computer language's date isn't always finito. Sometimes it's partial, like a half-eaten pawn galactic gargle blaster, or infinite, like the queue at the restaurant at the end of the universe. You start with the bottom. That's the ultimate I know bugger all state. Everything approximates from there, dilled up with partial orders, little finite guesses that get better, like saying it's sort of a spaceship until you nail it, as the Heart of Gold with a drive that turns you into a sofa mid-jump. The least upper bound ties it all together, ensuring your infinite streams of bad luck don't crash the system. Without it, recursion would loop forever without a fixed point, and we'd all be stuck in an endless Vogon poetry recital. It's what lets deep thought approximate the answer to life over 7.5 million years, starting from Zilchan lubbing its way to 42. Arthur frowned. "So, the universe is just a big, approximable domain." "Precisely." Ford grinned. "And don't panic, it's all continuous and monotonic. Better inputs, better outputs. Now, fancy approximating a real drink." As the ship hummed on, Arthur wondered if domain theory explained why his life felt like one big partial element, forever approximating normalcy. Domain theory is a comprehensive mathematical framework for defining the data values and primitive operations of a programming language. A critical feature of domain theory and expressive programming languages, like Scheme and ML, is the fact that program operations are also data values. Both operations and values are elements of computational domains. What is domain theory? A friendly intro. Hey there. Imagine you're trying to build a super smart way to describe how computer programs work under the hood, especially when dealing with tricky stuff like infinite lists, functions that go on forever, or values that aren't fully defined, yet like a half-baked idea. That's where domain theory comes in. It's like a mathematical toolkit for programming languages, helping us define what data really means and how operations crunch it. This PDF is a beginner-friendly guide based on some famous lectures by Dana Scott, tweaked by folks at Rice University, that explains it all without too much jargon. I'll break it down simply, like chatting over coffee. Why do we need this stuff? The motivation programs are all about taking inputs data and spitting out outputs using rules operations. But in fancy languages like Scheme or ML, things get wild. Functions can be data too, and some values are infinite, like an endless stream of numbers, or partial, like I know it's a number starting with 0, but that's it. The big idea. We can't always write these infinite things down in a finite way, so we describe them as a bunch of approximations, little finite guesses that get better and better. Each guess is like a puzzle piece saying something true about the final value. For example, a partial value might be a tree with some branches missing. A full finite value is like a single leaf with the number 42. Infinite ones are built by stacking these approximations forever. Domain theory makes sure all this works smoothly, so programs behave the same no matter how you represent the data. The building blocks, partial orders and CPOS, at the heart is something called a partial order. Think of it as a family tree, where some things approximate others. We use a squiggly symbol, called V here. Meaning is a rough version of. It's reflexive, everything approximates itself. Antisymmetric if A approximates B and vice versa. They're the same. And transitive if ABC, then AC. We care about upper bounds, things bigger than a group, and especially the least upper bound loop, the smallest thing that covers them all, like the simplest way to combine ideas. A complete partial order CPO is a partial order or every directed group, a set where you can always combine small chunks as in loop. There's always a bottom element, pronounced bottom, which is like I know nothing yet it approximates everything but says zilch. Finitary bases, the simple foundation to make domains countable so computers can handle them. We use a finitary basis, a list of basic propositions, facts about values. These are like logical statements. They're closed under combining consistent facts using loop as and. Empty set, that's true but useless. Examples, for strings starting with 0, propositions like 0 starts with 0, rest unknown, or O exactly O. If two facts match, their loop is the more specific one. From this basis, you build the full domain as sets of consistent propositions called ideals that are downward closed if something's true. Weaker versions are two-and handle combinations. Partial elements approximate others, for example, starts with 0 approximates O or O1. Total elements are fully defined and don't approximate anything else like exact numbers. Building bigger domains, products, functions, and more domains aren't lonely, they combine. Product, pairs of things from two domains, like number, string. Approximations work component-wise, sum plus, either from domain A or B, like a choice. Useful for tagged unions. Function space, functions from one domain to another. A function approximates another if it gives better outputs. For better inputs, monotonic and continuous preserves loops. These let you define recursive stuff, like trees. T equals atoms plus TT, meaning a tree is either a leaf atom or a pair of subtrees. Domain equations. Handling recursion, sometimes domains define themselves, like a list is nothing or a thing plus another list. These are domain equations, solved by finding a fixed point, the smallest domain that fits. It's like unfolding the definition step by step until it stabilizes. Finite elements. Built-in finite steps, no loops. Infinite ones. Limits of endless approximations, like an infinite tree. Making it computable for real computers, domains need an effective presentation, a numbered list of finite elements, where you can check if things are consistent, or find loops using algorithms. Recursive functions. Computable functions, ones where you can list input-output pairs step by step. Examples show how to make recursive domains like trees computable if the basics like numbers are. Wrapping up, why it matters. Domain theory is the secret sauce for understanding programming language semantics, how languages, like functional ones, handle infinity, laziness, or undefined behavior without crashing. It uses math to ensure computations are approximable, monotonic, better input equals better output, and continuous handles limits well. Think of it like baking a cake. Start with simple ingredients, finite approximations, mix them, rules, loops, and orders, and build up to fancy infinite layer cakes, complex data. No PhD needed, it's all about step-by-step improvements. Example from The Hitchhiker's Guide to the Galaxy. Imagine domain theory, like the infinite improbability drive on the Heart of Gold spaceship. Normally, spaceships move in finite, predictable ways, like finite data in programs, but the drive lets you jump to wildly improbable places by calculating infinite probabilities step by step. In domain terms, bottom, the starting point. Like don't panic, you know zilch about where you'll end up, just that something might happen. Approximations, finite guesses, like turning the crew into yarn or Sophie's mid-jump. Partial, weird states that hint at the final outcome but aren't there yet. Least upward bound loop, the drive combines these crazy approximations into the least improbable result, popping you out at your destination the total, fully realized value, like arriving at Milliways, the restaurant at the end of the universe. Infinite elements, the drive handles endless possibilities without exploding, much like domains manage infinite data streams. For example, an endless Vogan poetry recital, I building them as limits of finite chunks. And remember, the answer to life, the universe, and everything is 40 to a total element in the domain of ultimate questions, approximated over 7.5 million years, I deep thoughts computations. If only they had a better partial order for the question itself.